Good morning, class. My name is Mr. Kwok, and today I will be presenting a presentation on thermodynamics, its applications, and its uses. Thermodynamics is defined as the study of the direction and extent to which a process proceeds, and favors spontaneity, which is its procession to completion without outside interference. Thermochemistry is the specific study of spontaneity of the chemical processes only. This is not to be confused with thermodynamics and should be kept separate, although they are similar fields of study. Kinetics and thermodynamics are closely related in terms of achieving reaction progress, as seen on the graph below. And while kinetics is the study of reactivity according to the activation energy of a system, thermodynamics is the study of spontaneity and the stability of reaction. As you can see in the graph pictured below, the activation energy, or EA, of the system is the difference between its highest energy point, the peak, and its initial reactant energy, and this has kinetics field of study. And this is more to do with getting a reaction started and the energy required to input into the reaction to start, rather than thermodynamic study, which, as you can see, is the difference between the beginning reactant energy and the final product energy, and this is the free energy change, or delta G, and this will be talked about more later in the presentation. Spontaneity according to entropy. Entropy is one of the central driving factors of spontaneity, and it is defined as the increase in disorder that is naturally found in nature. For example, this includes moles of gas in a reaction increasing from reactants to products, dissolution of a solid into ions or aqueous solution, and evaporation of a liquid into a gas. And this would typically be marked with an increase in kinetic energy of the state of matter. A positive value of delta S is favorable. The delta S of a reaction can be calculated using the formula the sum of the moles of products times the entropy of the products minus the sum of the moles of the reactants times the entropy of the reactants, where each S is the absolute entropy in joules per mole Kelvin. As you can see in this example reaction below, nitrogen gas and 3 moles of hydrogen gas react to form 2 moles of ammonia in the Haber process, or the formation of ammonia. And delta S would be negative as the moles of gas increases from 4 moles of gas on the reactant side to 2 moles of gas on the product side. So the decrease in moles of gas would lead to a decrease in chaos and entropy. Also pictured in this image to the top right is an increase in entropy as the molecules become more dispersed and spread out. The spacing in the left side is more close to and resemblant of a solid, while the right would be a gas, and the left has more order while the right has less. Right has less order, and the left has more order. Different scenarios of entropy would include a gaseous substance having more entropy than a liquid substance, which would have more entropy than a solid substance. As you can see pictured in the top image, the moles of gas would have a greater speed of kinetic energy and chaos and entropy, while the liquid moles would have a less rigid structure than solids, but more ordered than gas and spaced together to a greater extent. The solids would be rigid and uniform in structure, and this would result in the greatest order and least entropy. A greater number of moles, assuming identical states of matter, would signify greater entropy, and a higher molar mass would mean more entropy. More molecular complexity would mean higher entropy, and this is difficult to explain, but it can be seen with comparing organic molecules and normal molecules. The complexity of organic molecules is typically greater in entropy values, and aqueous solutions would have more entropy than solids. This is an example of calculating entropy using the entropies of 2 molecules. According to the following information, find the standard delta S, and this is that little circle sign, of the reaction 2NO2 gas forms N2O4 gas. The entropy of NO2 gas would be 240.06 joules per mole Kelvin, and the entropy of N2O4 gas would be 304.29 joules per mole Kelvin. So, using the reaction or equation presented in the previous slide, you would find the standard delta S by subtracting 304.29 joules per mole Kelvin, which is the entropy of the product side, minus 2 times 240.062 joules per mole Kelvin, which is found because of the coefficient on the reactant side would be 2, and you would have to multiply the entropy of NO2 gas by 2. So you get 304.29 joules per mole Kelvin minus 480.124 joules per mole Kelvin. And this would give you negative 173.834 joules per mole Kelvin. And as the value of delta S would be negative, this would be a non-spontaneous or a non-favorable reaction to go towards spontaneity. And this makes sense as the moles of gas decreases. Let's now move on to a different property of thermodynamics, and it's enthalpy or delta H. Enthalpy is equal to the total amount of heat within a system. A negative delta H value would be an exothermic reaction and is normally favorable. A positive delta H value is endothermic, which absorbs heat from the surroundings and is marked by a colder temperature, while a negative delta H value is exothermic, releasing heat to the surroundings and is at a hotter temperature. Enthalpy can be calculated using both the heat of formation equation or the bond energies of compound equation found below, but they have distinct calculation methods. As you can see, the bond energies is the sum of the enthalpy of breaking the bonds, which would be in the reactants as you break bonds in reactants, and you would add that to the delta H of forming bonds, which would be in the products as you form bonds when you create a product. And the plus sign would typically is here, but it would be the forming the bonds would be an exothermic process and would result in a negative value of delta H, so you're basically subtracting. The heat of formation would be the sum of the heat of formation of the products minus the sum of the heat of formation of reactants. So you should need to make sure that for bond energies you're doing reactants minus products, while for heat of formation you're doing products minus reactants. This is an example of enthalpy according to bond energies, and in this reaction C2H4 gas plus hydrogen gas forming C2H6 gas, what is the delta H reaction of the above reaction? Now, we need to observe all of the different structures of these molecules, as you can see pictured up here, and we have different bond energies of specific molecules, so we need to use all of these bond energies in order to find the delta H reaction. So as you can see in the C2H4 molecule, there's a carbon-carbon double bond right here, so you need to break the carbon-carbon double bond in order to proceed throughout the reaction, and you also need to break the HH single bond here. But you would not need to break the 4 CH bonds since the final product would already have 4 CH bonds. So you would only need to break the carbon-carbon double bond and the hydrogen-hydrogen single bond. So you add 602 kilojoules per mole for breaking a carbon-carbon double bond and 436 kilojoules per mole of breaking a hydrogen-hydrogen single bond. And you would then add the heat of forming the reactant, or rather product bonds, and you could do this by the carbon-carbon bond energies being 346 kilojoules per mole, so you would add negative 346 kilojoules per mole as you're forming it. And as you can see in this structure, you have 2 more CH bonds and obviously this carbon-carbon bond, so you need to add 2 times negative 413 kilojoules per mole for the carbon-hydrogen bond energy. So in total, you would get 1038 minus 1172 kilojoules per mole, and the delta H reaction of the entire reaction would be negative 134 kilojoules per mole, which is negative and therefore exothermic and favorable of spontaneity. This is an example of enthalpy according to the delta H of formation, and in this reaction, 2NOG plus O2G forms 2NO2G. What is the delta H reaction of the above reaction? You're presented with these values for delta HF, and O2's delta HF would always be 0 kilojoules per mole. NO delta HF would be 90.25 kilojoules per mole, and NO2's delta HF would be 33.18 kilojoules per mole. The delta H reaction would be the sum of the delta H of the products minus the sum of the delta H of the reactants. So you would do the 2 for the coefficient of NO2 times the delta H of NO2, which would be 2 times 33.18 kilojoules per mole, minus 2 times 90.25 kilojoules per mole for the NO with a coefficient of 2, plus 1 times 0 kilojoules per mole for O2. So you'd subtract, and then you would get negative 114.1 kilojoules per mole for the delta H of reaction in total, which is also negative and exothermic and therefore favoring spontaneity. These are some of the laws of thermodynamics, which are extremely important conceptually in understanding the overall functions of thermodynamic systems. The first law of thermodynamics, which is equal to the law of conservation of energy, states that energy cannot be created or destroyed and constantly flows in and out of systems. The second law of thermodynamics states that the entropy of a closed system is always increasing. The chaos of the universe is also always naturally increasing, as the delta S of the universe, or entropy, would be greater than zero. The third law of thermodynamics states that the entropy of a closed system approaches zero as the temperature approaches absolute zero, 0 Kelvin or negative 273.15 Celsius, and this is the definition of absolute zero, which is the point where no more heat can be removed from a system. There's also a zeroth law of thermodynamics, which is when A equals B and B equals C for where A, B, and C are all different reactions, the A would equal C and they would all be in thermal equilibrium, but this is harder to conceptualize than the others. Now we move on to the final property of thermodynamics, and this is Gibbs free energy, or delta G. And this equation, delta G equals delta H minus T delta S, is one of the most important thermodynamic equations in all of AP chemistry, and it's extremely important to remember how to apply, even though it will be on your AP packet. Gibbs free energy is the ultimate deciding factor of spontaneity, as a negative delta G results in a spontaneous reaction. Exergonic reactions would be when the Gibbs free energy is less than zero, and this would be favorable, while energonic reactions would be when the Gibbs free energy is greater than zero and be unfavorable. The sign of delta G tells the direction of shift for an equilibrium, where a negative delta G would be a right shift in order to reach equilibrium, while a positive delta G would require a left shift to reach equilibrium. The magnitude of delta G tells how far standard state is from equilibrium, and a higher absolute value of delta G means a greater shift the reaction must undergo to reach equilibrium. This is a problem worked out using the delta G equals delta H minus T delta S equation, and given these three values, delta H equals 40 kilojoules, delta S equals 300 joules per Kelvin, and T equals 150 K, calculate the Gibbs free energy of the system and state whether it is spontaneously favored. Using this reaction, or equation, you would calculate delta G equals 40 kilojoules minus 150 Kelvin times 0.3 joules per mole Kelvin after converting 300 joules per Kelvin to, this should say kilojoules per mole Kelvin. And you would get 40 kilojoules per mole minus 45 kilojoules per mole equals negative 5 kilojoules per mole. And as delta G is negative or less than zero, the reaction would be spontaneously favored. So yes, it would be spontaneously favored. Now we can relate non-standard and standard delta G, and standard is with that little circle at the top looking like a degree sign, and this is at standard conditions, while non-standard is at like any conditions. And this equation would be marked by delta G equals delta G standard plus RT ln Q, and this would equate delta G and non-standard G to standard G, where R is the gas constant, which will be depicted later below in this example problem. And the reaction is 4NH3 plus 5O2 would result in 6H2O plus 4NO. And what is the delta G at 298 K? Well, the value of delta G standard is given, which is negative 955.6 kilojoules per mole, and all of the concentrations of the species are given, so you can calculate Q from there. The value of Q would be equal to H2O to the power of 6 times NO to the power of 4 divided by O2 to the power of 5 times NH3 to the power of 4. So that's this, which is 1.2 to the 4th times 1.5 to the 6th over 2.0 to the 4th times 1 to the 5th, which is equal to 1.5. So now you can plug in your value of Q, and you can get delta G equals negative 9.56 times 10 to the negative 5th kilojoules per mole, which is the delta G value, but this should be in joules, plus 8.314 joules per mole Kelvin times 298 Kelvin times ln of 1.5. And this would result in the delta G value being negative 9.6 times 10 to the 5th joules per mole, which is negative and would therefore be favorable. And this is also an equation that relates the standard G value to K, which it would be at standard state, or Q being the reaction quotient, which would not be at equilibrium. This is a chart of spontaneously favored conditions that should be memorized, or at least able to be applied to receive. And the favorable or spontaneously favored reactions would include, or conditions would include, delta H is less than 0, delta S is greater than 0, or delta G is less than 0. Unfavorable conditions would include delta H is greater than 0, delta S is less than 0, and delta G is greater than 0. I hope you learned from this thermodynamics presentation, and I hope you remember all these equations and you're ready to study for the AP exam.